Very good morning, my dear students. I welcome to my 8th class on the design of RC columns. In fact, today is the last class as far as the design of columns are concerned. In fact, I have 2 more classes wherein I will be discussing about the design of staircases, and that happens to be the last classes. Now, as far as the today's class is concerned, we will be discussing a few important problems in connection with biaxial bending. In fact, in the yesterday's class, we saw quite a good number of problems on the uniaxial bending of columns using SP16, and I also just introduced to the concept of the behavior of a biaxially loaded column. So let us see as to what this biaxially loaded column as far as its design as per IS 456-2000 is concerned. So this is what is referred to as the Bresler's load contour approach method. In fact, I explained about this equation in the yesterday's class, and this is what the interaction equation we need to satisfy as far as the biaxial behavior is concerned. And here MUX and MUY, if you can see in the 2 parts of the equation, the first one is MUX, and here in the second part we have MUY. These are the 2 moments given in the problem. So they are the design biaxial moments, and that's what I have mentioned here. So MUX and MUY, moments about x and y axis due to design loads, and whereas MUX1 and MUY1, they are the maximum uniaxial moment capacity for the same axial load PU. So in fact, in order to get this MUX1 and MUY1, we need to refer to SP16, the uniaxially loaded interaction curves. And we also have this alpha n, a factor you can see in the equation, and this is a function of PU by PUZ. So that is what the, again, the non-dimensional parameter, and PU is what the ultimate load given in the problem, and PUZ is the absolute maximum load carrying capacity of the same column provided there is no moment MUX and MUY. In fact, that is what the formula PUZ. So this has been given like this, and this is there in our IS 456 and also in our SP16. In fact, this is not going to take the eccentricity of the column into consideration, and if the eccentricity is introduced to this, as I told you in the yesterday's class, so this has to be reduced. The value of PUZ, if you reduce it by about 10 to 11%, we are going to get PU, which is the practical load on the column. And how to identify this alpha n? In fact, this alpha n is a function of PU by PUZ, and PU by PUZ practically varies from 0.2 to 0.8. And if it is 0.2, as I told you, it is 1. As far as PU by PUZ equal to 0.8, the alpha n is 2. In fact, this alpha n varies linearly from 1 to 2 depending on PU by PUZ varying from 0.2 to 0.8, as you can see in this particular graph. So if the value of PU by PUZ, if it is less than 0.2, so you can take alpha n as 1. As you can see in this red line, it is assumed to be constant over this range, and similarly if PU by PUZ, if it is greater than 0.8, then alpha n is taken as 2, and for any intermediate value you need to interpolate. So in fact, we have studied the interpolation in your earlier semesters also. So you can use this interpolation concept, or you can also use this simplified equation, which will give you the value of alpha n for any value of PU by PUZ. And what is this interaction equation is all about? So this is what the interaction equation you can see here, and if the value of alpha n is taken as 1, and this is just a 2 component of the equations, they vary in the linear form. It is something like x plus y combination. And if you see in the y axis, it is simply MUY upon MUY1, and in the horizontal axis, the x axis, it is MUX upon MUX1. If the value of alpha n is equal to 1, which is corresponding to PU by PUZ equal to 0.2, the interaction equation is a straight line. You can see here, this is what is referred to as the envelope or the interface. The interface for the interaction is linear. Now, as the value of alpha n increases from 1 to 2, so So obviously we need to increase these two values, raised to the power of alpha n, obviously, so it becomes non-linear. A little bit of non-linearity to start with, and then depending on whether the alpha n is very close to 2, then it is highly non-linear. So this is what the circular interface you are going to get. I have drawn few such interaction envelopes as the alpha increases from 1 to 2. Now what is important in satisfying this interaction equation is, so we can do this problem simply by calculating all the needed information and finally substituting the information in this equation and satisfying this value whether it is less than or equal to 1. If it is just less than 1, it is safe but also economical. If it is significantly less than 1, it is no doubt safe but it is highly uneconomical. So we need to look for such a combination wherein we can adjust the size of the column, or we can even adjust the percentage of reinforcement or the grades of the material to see that ultimately we end up with this equation equal to 1 or slightly less than 1, so that it is not only safe but also economical. Now a similar type of graph what I have shown here is also available in SP16. So straight away you can use these interaction equations and satisfy whether satisfy all the requirement, and so that you can check the adequacy of the column. To do this, in fact you see here we have three values of the interaction parameters. One is mu y by mu y1, mu x by mu x1, another is your pu by pu z. Now for any two values of these three parameters, for example mu y1, mu by mu y1 and mu x by mu x1, and you get a point, and if that point lies within the envelope of pu by pu z, then it is safe. Or for a particular value of mu by mu y1 and also for a particular value of say pu by pu z, and you would find out what might be the maximum value of mu x by mu x1 that can be allowed for your problem. And if your actual value of mu x by mu x1, if it is less than the limiting value of mu x by mu x1 found from this graph, then also it is safe. In fact, I will be discussing two problems today, so wherein I will be using all these interaction equations straight away, and of course the use of these envelope from SP16. What that SP16 graph you have? This is what the blown up view of the graph that is available in your SP16, because some of the things are not very clear, so that is the reason why I drawn the graph separately, and this is how the SP16 graph looks like. So all those parameters what I explained in the previous graph, so this is what the graph, the same thing you can see here as well. Now let us see some of the design example to start with. So the first problem goes like this: design a suitable reinforced concrete section of the column of an effective length 2.85 meter to resist a factored load of 250 kilonewton along with factored moment of 35 kilonewton meter about both the major and minor axis. Use M20 concrete and Fe 415 steel. Take the size of the column as 250 by 250 mm. In fact, in this particular problem, the size of the column is given, and sometimes the size will not be given, and you may have to start with some arbitrary size depending on whether the square is required or circular is required or the rectangular column is required. In fact, if you see the loads, they are all the ultimate loads or the critical loads. No need to multiply with load factor. Now since the effective length of the column is given, so we need to check whether the column is a short column or a long column. Long column, as you know, is also called as the slender column. If the column is slender, then the slenderness effect and the additional moments are to be considered in the design. Anyway, that type of problem we are not discussing as it is not included in the syllabus. Now for this effective length of 2.8 meter, if the column is short, then what the procedure we are following is valid. And also you need to check whether the minimum eccentricity moments are less compared to the given moments, then the given moments are to be taken. Otherwise, the minimum eccentricity moments governs the design. So in order to determine the minimum eccentricity, we need the unsupported length of the column also. If the unsupported length is given, take that length, and sometimes the unsupported length is taken equal to 2.85, which is the effective length of the column, provided the ends are assumed to be hinged. Otherwise, the effective length and the unsupported lengths will be different, and accordingly we have to calculate the needed informations. Now coming to the data given, factored load PU is given 250 kilonewton. It is just 25 tons of load. In fact, 250 kilonewton is a very small order of load, as you can make out, and probably a very minimum size of the column may be okay, and that is the reason why 250 by 250 mm is given. The factored moment MUX and MUY both equal to 35 kilonewton meter, and the grade of the concrete is M15 and that of steel is Fe415. There is a small mistake. So the grade of the concrete is M20 in the problem. So here I have written it as M15. It is not M15. So M15 is for one of the other problem which I will be discussing, but it is M20 concrete. Obviously FCK is equal to 20. In fact, I have done all the calculation for FCK is equal to 20. Now this is B equal to D equal to 250 mm. So unsupported length is what this is. So the effective cover to the steel is 25. 25, as you know, it is the clear cover or the nominal cover for the column. For column in general it is 40 mm, but there is a specific specification. If the column size is 25 and less, so you can take 250 mm or less, you can take 25 mm as the clear cover. So that is why I have started with 25 mm clear cover, because the size of the column is 250, and plus half the diameter of the bar, assuming 20 mm dia, it is roughly 35 mm. So that has been increased to 40 mm. So 40 mm is what the effective cover, and you can even increase the effective cover marginally depending on what order of cover that is required in practice. Now with this effective cover, and also by assuming the reinforcement distributed on all the four sides. So this is what I am assuming, because the column is square, so that I can put the reinforcement in all the sides. D dash by D, the effective cover to the depth ratio, 40 by 250. So this is nothing but 0.16. So 0.16 is close to 0.15, and the chart corresponding to 0.15 is to be used. And also you see LE by D, the slenderness ratio of the column with respect to the side, 2850 by 250. So that is 11.4, less than 12. So the column is short. So in fact the column is very close to 12. So it is a short column only. So by chance if the length is different, then since the size is small, so obviously it may even work out to be slender. So that is the reason why we need to identify all these parameters such that the column is either short or long depending on what is required in practice. Eccentricity check. In fact, in some of the earlier problems in connection with uniaxially loaded column, I have simply assumed that the minimum eccentricity moments are rather less. But here I am just trying to make a check to see that which moment is higher. Now the given moment is mu and the given load is pu. So mu upon pu, as you know, it is what the eccentricity. Ex is equal to Ey because it is a square column, and 10 to the power of 6 multiplication for moment and 10 to the power of 3 for the load, and with this you get 140 mm. So what is this minimum eccentricity is? That is nothing but unsupported length divided by 500 plus the depth of the column divided by 30. In fact, this eccentricity has to be checked for both the axis, major as well as minor, since it is a square column, and also unsupported length taken to be equal to effective length for both the axis of bending. So we have the same minimum eccentricity. So the minimum eccentricity as per the calculation, by substituting these values, it is 14.03 mm. But code says that we need to design for some minimum value, that is 20 mm, or whichever is greater is what the criteria. So out of these two, 20 mm is what the eccentricity. But the eccentricity, because of the applied moment, you can see here mu by pu, it is 140. So the minimum eccentricity is significantly less than the eccentricity due to the design loads. So we need not have to worry about the minimum eccentricity. So you can simply go ahead with the given moments as the design moments. Now P by FCK is 0.1. This is one of the parameters that is required for referring to SP16. P is the percentage of steel upon FCK. So here we have taken the percentage of steel approximately equal to 2%, and PU by FCK BD. Pu by FCK BD. So this is nothing but 0.2. So you can just see after the substitution it is 0.2. Now as per IS 456-2000, so we need to calculate this absolute load carrying capacity PUZ 0.45 FCK AAC plus 0.75 FY ASC, where AC, the area of the concrete, is the gross area of the concrete minus the area of the steel. Now assuming 2% of steel, so this is what is the steel to start with. In many of the problems we will not be knowing as to how much of steel is to be used to start with. So I suggest the students to use a value very close to 3%, and once the problem is checked for the adequacy, and later with one more trial, so we can identify the probable value of the reinforcement percentage. Or as I told you in one of the previous classes, we have to identify the equivalent moment under the root of mx square plus my square and amplify that equivalent moment by about 10-15%, and then taking that equivalent moment along with the given load and identifying the two non-dimensional parameters, and by using the interaction curve for the uniaxially loaded case, so we can identify the probable percentage of steel that can be provided. So with that steel, again if you do all these checks, so probably your column is going to be safe. So that is how we have to do it. So instead of doing that, anyway some calculations are involved in both the approaches, but I am just starting with 2% of steel so that we can check the adequacy. So with that 2% of steel, what the 2% is? 2 upon 100 into 250 into 250, it is 1250 mm square. With that PUZ, after the substitution into this equation, so you can see the relevant values being substituted properly. So it works out to be 940 into 10 to the power of 3 Newton, that is 940 kilonewton. So therefore Pu by PUZ works out to be 0.27. With this alpha n is I have interpolated it, as you can see, starting from the minimum value of alpha 1 for 0.2. So for 0.8 it is 2. So obviously the difference is 2 minus of 1 in the numerator. In the denominator it is 0.8 minus of 0.2. This is what the information we know. And what is the difference in Pu by Puz of our value corresponding to 1. So our value is 0.27 and we started with 1, which is 0.2. With this it is 1.12. It is a very simple interpolation. Now P by FCK is 1. So therefore we need to use the chart number 45 of SP16 for picking the probable value of the another parameter in connection with mu. The value what I have got from the chart is 0.14. I will show you this 0.14 in the chart later. So mu x upon FCK BD square is nothing but 0.14. This is what the value we are looking from the chart, uniaxially loaded chart, and with this mu x is nothing but mu x1 and mu y1, the absolute maximum value of mu x1 or mu y1, where you have the eccentricity either with respect to the major axis or only with respect to the minor axis. So that works out to be 43.75. So in fact this moment is going to be substantially higher compared to the given moment. So the given moment is 35, but it is 43, and if you take the ratio of one to another and then rise to the power of alpha n, probably your interaction equation is not going to be satisfied. Now let us see how this 0.14 can be determined from the interaction equation corresponding to your Pu by FCK BD equal to 0.2, and of course the probable curve is P by FCK equal to 0.1, because we started with 2% of steel and for which P by FCK is 0.1, and you can see your 0.1 laying here. So in fact I have encircled that value of 0.1, which you may not be able to see in this transmission, but corresponding to that, so if you simply run along this particular line corresponding to P by FCK, you kindly see the cursor how it is going, and corresponding to 0.2, this is what your 0.2, and going up to the point corresponding to your interaction curve for P by FCK 0.1. So you have a point somewhere here and then draw a line vertically down to pick up the point on the horizontal axis. What that value is? that is Pu divided by FCK BD square. In fact, that value is 0.14. So, that is what the value I have used here, 0.14. With that I have got 43.75 as the moment. Now, if you substitute these values, what these values are? One is a given moment mu, another x, another is mu y, and upon mu x1 and mu y1 raised to the power of alpha, alpha being 1.12, and your interaction value is 1.56. In fact, your interaction equation is nonlinear, highly nonlinear, and that is greater than 1, so therefore it is unsafe. Now we need to increase the percentage of steel. Students, please see here. We started with 2% of steel, our interaction value is something like 1.5. Now we need to reduce this 1.5 by about 50%. So what I do next is to increase my reinforcement approximately by about 50 to 60% or so. I really don't know whether it is going to be satisfied or not, but I have tried with 3% of steel. There is no point in trying with 2.5%, 2.75%, things like that. So go to one more percentage like 3%, check whether it is okay or not. Probably it is going to be okay, otherwise one more check with still increasing the steel, you will be able to do the design. Now corresponding to this 3%, your PUZ, you need to substitute only 3% of steel here, which is nothing but 3 upon 100 into 250, 1875. So you can see the substitutions. So it is 1128 kilonewton. So therefore Pu by Puz, it works out to be 0.22. In fact, Pu by Puz keep on changes because you are increasing the value of steel, percentage of steel, so that your Puz is increasing. So definitely numerator upon the increasing value of Puz, so this value in fact decreases. Now corresponding to this 0.22, what is alpha n? So this 0.22 is rather close to 0.2. For 0.2, as you know, alpha n is 1. Since it is slightly more than 0.22, so probably your value is slightly more than 1, and if with this interpolation it is 1.01. P by FCK, it is 0.15. So 3% is what the present value. Now it is 0.15. So from the same graph, P by FCK equal to 0.15, we need to pick up the corresponding parameter associated with MUX. What that value is? So that value is 0.18. So corresponding to this 0.18 obtained from SP16, so your moment is something like this, 56.25. So your given moment is 35 and 35 with respect to both the axes. So this is the limiting moment, uniaxial capacity 56.25, 56.25, one upon the other, raised to the power of alpha n. With this it is 1.23. Still it is greater than 1. Therefore it is unsafe. Now 1.56, we wanted to reduce it to something like 1, but we increased the steel by about 1%, 2 to 3%. With that my interaction value is decreasing from 1.56 to something like 1.23. So probably if I increase the steel by another 1%, 1.23 can be reduced to a value very close to 1. So that's what I have done, and this is again the same interaction equation, the same chart to pick up the value of this parameter. So corresponding to same 0.2 going up to P by FCK equal to 0.15. You can see here 0.14 and 0.16 you have the line. For 0.15 you don't have the line. You can pick up an approximate line in between that and pick up the point corresponding to Pu by FCK BD equal to 0.2, and then run a line so that it cuts the horizontal axis. Corresponding to that another parameter is 0.18. This is what 0.18 we used, and the interaction value has been checked. With 4% steel, what happens? 4% steel means 2500 mm square. For that your PUZ, you can see here it is 1318. It has increased further. Therefore the ratio of Pu by Puz, it increased further. Sorry, it has decreased further. It is 0.189. So this is definitely less than 0.2. If it is less than 0.2, your alpha n is 1. With alpha n is equal to 1, your interaction curve, the envelope, is a straight line. So Pu by FCK, now it will be 0.2. So therefore from the same graph SP16, so what is the MUX by FCK BD square? which is nothing but 0.22. Let us see how that 0.22 can be obtained. So from the same interaction equation, going to this particular graph, so this is what the graph corresponding to 0.2. We can see here 0.12, 0.14, 16, 18, and this is what the graph corresponding to 0.2. In fact, you can't see in my graph, but this is what the curve you can see, and from that point, if you go down and picking the value as 0.22, so you will be able to calculate that MUX. With this, MUX1 and MUY1 equal to 68.78. So in fact, so we are trying to increase this value of the moment every time, so that your denominator value increases, so that the ratio is less when you raise that smaller value to the power of alpha n, so your interaction value keep on decreases. Now with this, your interaction value is rather very close to 1. It can be taken as 1. I don't think any further modification is required. So 4% of state is what the state that is really required, which is 2500 mm square. Now it is a square column. Decide about the diameter of the rod. If you go for 20 mm rod, you need 8 bars. In fact, in square column, it is better to have 4 or 8 so that you can think of proper links internally or the ties, depending on whether the closed links or the open links are required. So with this, the steel provided is 2512, exactly equal to the value what is required. Now, how the arrangement of the reinforcement is going to be. To identify that, first we need to design the transfer steel. So the diameter of the tie is 1/4 of the diameter of the main steel, which is 5 mm, but minimum to be used is 6. Greater is what they 1. So you can go for 6 mm mild steel, but in practice 8 mm is what is available, which is the ribbed bar of Fe415 or 500 depending on the situation. Now the spacing, minimum of these three, less than 300, the spacing should be 16 times the diameter of the bar, maximum dia of the bar in fact 320, least lateral dimension being 250. Here 250 grams the spacing, therefore provide your tie 8 mm dia at 250. When you provide, your arrangement is going to be like this. But many a time the students will be simply providing 2 internal ties, or they may provide 1 diagonal internal link, but all those things are going to be wrong. But you have to see whether open link or closed link is required. Or you can also identify whether any link can be avoided internally. Now for that, what is important is the distance between any 2 successive bars. Of course, you need the distance between the 2 end bars, corner to corner bars, along X and also along Y. So your effective cover of 40 and 40, if you remove, it is 170. Since this 170 is less than 300, you need not have to provide any reinforcement in between, but we have gone for more number of bars, so I am providing 1 bar, so nothing to worry. But what is the distance again? So that is half of 170, that is 85. Now since this distance is 85, which is greater than 75, it is not less than 75. Code says that if the distance between the successive bar, if it is less than 75, so that particular bar can be avoided from tying, so that the rest of the bars can be tied depending on the situation. But now, since it is more than 75, I can't avoid, so I need to tie all the bars. Now to decide whether open link or close, you need this distance. That distance is, you can see 170, but 48 times the diameter of the bar is what the criteria, which is 384. In fact, this value of 170 between the corner to corner bars is less than 384. So obviously we have very less concrete in the core to confine. So open tie is sufficient. What is the configuration? 1 tie plus 2 open links. So this is how you need to identify the internal configuration of the tie depending on the number of bars. And maybe if you go for still more number of bars depending on the situation, instead of 8 of 20, we can think 16 mm or even 12, then we will be having number of bars, and in that case the distance between the 2 bars will definitely be less than 75, and in that case we can eliminate the alternate bars from tying. Now if you see here, there is a small difference, 85 and 75, it is hardly 10 mm, 1 centimeter of difference. If that 1 centimeter of difference, not a big difference, if you can account in the cover, if you can increase the cover marginally from 40 to something like 45 or 50, and this distance decreases. You decrease it in such a way that it is exactly equal to 75 or slightly less than 75, so that you can eliminate this in between bars from tying. If that is the case, your configuration is going to be like this. If the effective cover is increased marginally, say 50 mm, of course, as far as the design is concerned, we have to look for an entirely different graph, that is d dash by d equal to 0.2, but in the previous case it was 0.15. You will not be having much difference in the reinforcement, but what I want to tell you is, if you can increase the cover marginally in this particular problem, which is a practical problem, so altogether internal open ties can be eliminated. So that is going to be a significant saving if you look the problem in that particular direction. Now this is one tie configuration. That is what one tie covering the four corner bars with proper links. So in fact I have told you as to how these links are to be provided, what is the angle and what projection and all these things need to be appreciated, and accordingly you need to produce the drawings. And this is the situation where I am not going to provide any open links. Let us go to the second problem, which is on the rectangular column. The problem goes like this. Determine the reinforcement to be provided in a short column, and he has already given the column as short, otherwise we need to check, and that is what we did it in the previous problem. Subjected to biaxial bending with the following data. Size of the column 400 by 600 mm. If you see this size, the previous size was 250 by 250, very small, but here the shorter dimension itself is 400, significantly higher. Upon by 600 means definitely your column is able to carry significant load and moment. And the grade of the concrete is M15. From M20 it has been reduced. Characteristic strength of steel is 415 megapascal. Factored load is 1600, again it is PU, and similarly MUX. Factored moment acting parallel to the longer dimension. Moment parallel to the longer dimension means it is what the moment acting parallel to the longer direction. You can see here, this is what the longer direction. With respect to the longer direction, you have the moment, means your column is going to bend with respect to the major axis, and that major axis is what the axis which is parallel to the smaller dimension. Means in this particular case, your MUX being the moment with respect to the major axis, and another moment is with respect to the minor axis. Major axis moment is 120, minor axis moment is 90. In fact, it is given as MUX and MUY. You can make out, even otherwise also you should be able to make out the information. Just because one moment is maximum, don't simply think that that moment is always corresponds to MUX. Need not be. So shorter dimension might be having more moment and vice versa. This is another assumption. Moments due to the minimum eccentricity are less than the value given, and it is quite obvious. And if you see your moment, that is 120 and 90, if this moment is divided by this load 1600, you are going to get a value which is definitely more than 100. So minimum eccentricity is hardly 20 mm. So these given moments are definitely higher compared to the moments because of the minimum eccentricity. You need not have to do any check because the condition is already given in the problem. Again, let us take the reinforcement distributed equally on four sides. So why I am distributing the steel on four faces? Because it is a biaxial case. Moments are there on both the faces, on both the axes. So it is better to have this four side distribution. We can also look for two face also, but probably you may have to provide slightly more steel because we are going for two face, but the moment is also there onto the other face. The first trial section with a percentage of steel is roughly about 1.2. In fact, this is what the problem worked out in SP16. The same problem I have taken because most of you have this SP16, so that you can go through that problem and appreciate. After I explain this problem, if you just go through that problem, probably in just one glance, so you can feel the importance of the problem and you get the confidence for working out other problems. P by FCK, FCK being 15, it is 0.08, and your D dash 40 being the effective cover, and plus 25 by 2, it is 52.5. This is what the procedure used in our SP16. In fact, I have told you many times about this. So effective cover is nothing but the clear cover or the nominal cover to the tie, in fact. But what SP16 defines the nominal cover as, it is the cover to the face of the mine reinforcement. It is not going to consider the ties. So that is why I am taking this 40 as if it is the nominal cover for the mine, plus I am adding of the diameter of the bar. You can also take this 40 mm as the nominal cover to the tie, plus you can add one diameter of the tie and then of the diameter of the mine bar. Then your cover is going to be higher. So as the cover increases, then your internal steel is definitely safer from the environmental point of view. So probably that is the reason why in most of the textbook the effective cover is defined by taking the nominal cover to the ties rather than to the mine reinforcement. Anyway, that is a small variation, so you need not have to worry much. Uniaxial moment capacities are to be calculated as usual, one with respect to XS. For that, d dash by d equal to 52.5 upon 600, that is 0.088. So the chart corresponding to d dash by d, when you round off this to 0.1, this is very close to 0.1, that can be used. In fact, when you round off this to the higher value, the steel what you are going to provide is increases marginally. So that is why knowing this what sort of a modification you are going to make here, when you are providing the reinforcement, and even if the reinforcement is slightly less, probably your column is going to be okay. So that is where you have to appreciate to what extent this d dash by d has been rounded off to the next higher value. So Pu by FCK BD, so with substitution 0.444, 0.45. So referring to the chart 44, so you need to get this non-dimensional parameter with respect to moment, which is 0.09. So with that 0.09, your uniaxial moment capacity with respect to X is 194. Now this is how you can get it corresponding to this, and of course this is how it is going to be. So your mu by FCK BD square is 0.09. Now let us calculate the uniaxial moment capacity of the section with respect to the YY axis. So here d dash by d is going to be 0.131. It is higher because previously we worked with 600, now it is with respect to 400. The chart is different, it is not the same chart. That is where you have to be very careful. Referring to the chart 45 now, the value is 0.085 as far as mu is concerned. So therefore mu y1, this is what we are calculating, mu y1, because it is with respect to YY axis. The same value of 0.083 and substituting the remaining 2. Here we have to be careful. BD square. So your B is the larger value, D is going to be the smaller value. So as far as the major axis is concerned, it is small b capital D square. Here it is capital D into B square. We simply need to change this square. Instead of squaring 600, here we need to square 400. With that, it is 119 kilonewton meter. This is how we have to pick up the value. So the value is 0.83. Calculation of PUZ. So in fact, in the previous problem, this PUZ has been calculated because we have the expression for PUZ, but SP16 also gives a chart for determining PUZ. I just wanted to tell the student about this. So that is why this particular problem has been worked out with that chart. Percentage of steel is required for that, 1.2%. Fy and FCK are the two parameters, and of course PUZ by Ag is what the value you get from the chart, which is 10.3, so that when 10.3 is multiplied with Ag, you can get PUZ. PUZ is equal to 10.3, the value what you got from the chart, into 400 and 600, you get 2472. But how to get this 10.3 from PUZ by Ag? This is the value to be picked based on these three information. See the chart. We need chart 63 of SP16, and this is how your chart looks like. You may not be able to make out all the details, so go through SP16 and appreciate and see the details for which this chart is valid. And I have blown up this particular portion that looks like this. So here we have AS by Ag going from this point, this is the origin, 0.012 like that, area of steel by Ag, percentage of steel, 0%, 1%, 2%, like that it goes. Then you have PUZ by Ag, so that varies from 5, 10, 15, 20, like that, vertically downwards from this particular origin. And if you see from this particular reference line, we have these inclined lines, The top inclined lines corresponds to the grade of steel, Fe 415, Fe 500, Fe 250, like that. On the bottom 3 inclined graphs corresponds to the grade of concrete. The first one is for 15, second one is for 20, like that it goes. Now, what is our value? Our value of AS by AG, so that is 1.2%. This is 1%, 0 to 1% we have, you can see here how many lines are there, 5 lines are there. So, the next line is 1.2, draw horizontal so that it touches your graph. So, it touches this particular graph corresponding to my value of 4 on 5. This is for 500, 4 on 5, and this is for 250. So, it is touching 4 on 5. I am going down so that it touches FCK line, that is the first line, and then go horizontally and pick up the value. So, if you see the value 5, 10 and slightly more than 10 is what the value, that is 10.3 approximately, and that is what this 10.3 with that 2472 is what my PUZ. Now, how to check the safety? Now, I will be using the interaction equation, which is in the form of a graph. Chart 64 has been referred for that. What I do is, out of these 3 values, MUX by MUX1, I have the ratio, MUY by MUY1, I have the ratio, PU by PUZ, I have the ratio. In fact, I have calculated the value of alpha n also. You can calculate that. The equation itself can be used, but let us see how to use the graphs. So, for these 2 values, I will be checking the first value, whether I will be getting a value of 0.62 and less. That is how I am going to start. So, I first pick up the value corresponding to Y ratio 0.75, and then I pick up the value corresponding to P ratio, that is 0.65. Then what is the probable value of the parameter corresponding to MX ratio? If I do that, referring to the chart 64, the permissible value of MUX by MUX1 corresponding to the other 2 values is 0.58. This is what the value I am getting from the graph. That is what the limit in fact for the adequacy of the section. But what is my value for my moment of MUX1? MUX by MUX1 is 0.62. So, this is higher, but what value, that is the limit, is 0.58. So, since 0.62 is more than 0.58, so it is going to be unsafe. The actual value of 0.62 is only slightly higher than the value read from the chart, so it is unsafe. Since it is slightly higher, so probably you can increase the size of the column if there is an option, increase the grade of the concrete if there is an option, but otherwise in this problem, as an examination problem, we do not have any other option except to increase the percentage of steel very marginally from 1.2%. Maybe if we can increase it to something like 1.3% or 1.4%, it is going to be okay. So, that is what the problem is going to be. But let us see what is the interaction value. By chance, if you use these values in the interaction equation, after calculating alpha n, what happens? So, this is what the graph, just for the curiosity, MUY by MUY1 is 0.75, and then I have picked up the point corresponding to PU by PUZ is equal to 0.65. If I go down, I will be picking the value of MUX by MUX1, which is 0.58. That is what the limit, but my value is more than that. Since it is away from the interaction value, so it is unsafe. I want the value to be well within the interaction graph. So, definitely I need to reduce my value, which is significantly less than 0.58. With this Brewster load contour equation, so PU by PUZ is 0.65 in this case, corresponding to this your alpha n is 1.75, and use this alpha n in this equation. So, these 2 values, MUX by MUX1, MUY by MUY1, so that has been already calculated. So, you can see those values. So, here we can see these values 0.62 and 0.75. Now, if you put it here 0.62 and 0.75, it is 1.04. It is rather equal to 1, that is what I can say. There is not much of a difference, but still it is slightly unsafe. So, what I have done is I have increased the steel from 1.2% to 1.3%, and for that 1.3%, the total steel required is 3120 mm square. So 31.2 centimeter square is what the number of, is what the steel that is required, and then we need to identify the number of bars. The number of bars mainly depends on the diameter, and depending on the diameter and the number of bars, so we have different arrangements that is possible for your 4-phase, whether you are going to put more bars along the longer direction or the shorter direction. All those things need identified, and then only the configuration of the stirrup comes into picture, whether it is a open tie or a closed tie. Now again I have made the check, but you need not have to worry about all these things. So by providing 1.3%, I have repeated the problem just to have a glance. P by FCK now will be 0.086, and your D dash by D is 0.1. Again going to the chart 44, your MUX1 is 205. Similarly from chart 45, because 45 means definitely your D dash by D is 0.15. So with that MUY1 will be 122.4, and from chart 63 as usual, so PUZ by AG is 10.4. So therefore your PUZ is 2496, and these are the three values required so that we can see whether the interaction is going to be satisfied or not. So again I am checking this MUX upon MUX1, which is 0.585, but what is the limit from the graph based on these two? So based on these two values referring to the chart, the limit is 0.6, but my value is 0.58. So since 0.58 is less than the limit 0.6, so my column is safe. Again by using the Bresler contour equation, so it is 1.735 is what the value of alpha n corresponding to PU by PUZ of 0.641, and substituting in the equation it is 0.98 less than 1. So it is safe and very, very economical. So with this steel, the number of bars, so 10 bars of 20 mm dia, so steel provided is slightly more than what is required, so it is okay. What about the transfer steel? So 8 mm stirrup at 300 mm is okay, but what the arrangement of steel going to be? The sketch. As usual, identify all these things. Effective cover, what is the distance between the corner bars along the shorter as well as along the longer. Now if you see this distance corner to corner, it is 290, less than 300. You would have avoided this, but since the numbers are more, I have put 1. But what is this distance? So this distance is 145, more than 75. I need to put the tie. But what is this distance corner to corner? 290, that is less than 48 times the dia, so it is open tie. As far as the shorter direction is concerned, for these two rods it is a open tie, but as far as the longer direction is concerned, see that longer direction, out of 600, if you remove the two covers, it is 490. In fact, this 490 is greater than 48 times the dia of the tie, which is 384. So definitely you have more concrete in the longer direction, so you have to confine that concrete in that direction by putting a closed tie, not the open tie. So what this arrangement is going to be? In fact, we have one closed tie covering the 4 red bars and another one closed tie covering the block bars, means it is 2 tie arrangement plus 1 internal open tie. So this is nothing but 2 ties plus 1 open tie arrangement, and this is what the arrangement of the bar going to be. So this is what is important in the examination. Along with that, you can write the elevation of the column for about a meter or so, and then show some of the stirrups, how exactly this red and this block and this blue, because all the 3 stirrups will be at that particular level at a distance of about 300 mm center to center. So all the details should be shown in the examination. So with this I come to the end of this biaxially loaded column. So thank you very much, students. So what we have done is, so the chapter on design of column has been covered completely. So I think I have not left anything. So you can go through my materials. The material has already been handed over to the VTU site. So it is going to be put in the website. Go through all the problems and check whether you can understand everything. And you can also call me over phone. You can even send an email. So I have given my email address so that we can interact. So with this, I thank the student, and in the remaining 2 classes I will be completing the design of staircases, that is tomorrow and day after tomorrow.